Hello, Thermodynamics lab this week. If somebody says thermodynamics, what comes to your mind? For me, delta H, delta S. Those are the two important ones because I can derive the others. For example, if you give me the temperature and the reaction and delta H and delta S, I can derive the equilibrium constant at that temperature and also be able to state what the Gibbs free energy is. All right, so let's think about our reaction this week. One slide show. All right, pick up a pen here, pen pointers, pen. So we're blue this week. Blue, wonderful color. So we're going to look at determining K, the equilibrium constant for a reaction, delta H and delta S, and then from that figure out everything else. So we have our reaction that involves complex ions. You guys will be talking complex ions in the coming week. So basically this is cobalt hooked up to chloride, and PR is propanol. So this is one species here, and it's tetrahedral. Here's the other one, cobalt chloride, 2 propanols, 3 methanols. We are talking alcohols here. And so the reaction is from a tetrahedral species to an octahedral species, and if you look at the change, the net effect is just adding, removing 1 PR and adding 2 MAs. Trying to move my screen forward here. My goodness. Okay, there we go. All right, so how do you get all these goodies? Main goodies, main goodie, delta H and delta S. Enthalpy, entropy. How do we do that? Well, in our case, at least for this lab, we will determine K, the equilibrium constant for that reaction, as a function of temperature. Because if you do that, then with a little calculation here and there, you can derive all the other goodies. K as a function of temperature. All right. Well, we know all these things here, so we'll move on. So here's the reaction, right up there. Here's a tetrahedral species. It is blue. Tetrahedral in this case, think of it as being bonding to 4 things. And then we're going to add the methanol. So the methanols here all come in and kick out one of the propanols. Methanol, propanol, alcohols with an OH. So that's a reaction. Certainly easy to write the equilibrium constant for the reaction. There it is, just the 3 here. I mean, let's say there's 3 here, so that's cubed here. Yeah, you know the story. So when I determine that, we want to know this thing here as a number. As a number. Number. Oh, this doesn't work here. There. The number. We want to be able to do this at various temperatures. It's a lot of calculations, but Excel can do that for us. So it turns out here, this is just a color thing. This is the blue, as you call it. It actually trends to the other version, the pink, and so the equilibrium shifts to the right-hand side as you actually call. All right, so how are we going to do this? First of all, think of that equilibrium constant. 2 of the things we'll need is the concentration of the propanol and the concentration of the methanol. It turns out that those are easy. Let's go back here. We're looking at this. See, what's this term here? And what's that one there? Yeah. But those are easy. Because it turns out that our equilibrium mixture will consist of 5 mL of propanol total, 5 milliliters. and then 1 milliliter of methanol. Well, if we know that, and these are liquids, of course, and we're given the density, then we can figure out what the concentration is. Okay, 5 milliliters is the density, grams per milliliter, and then the molar mass thing, and then the total volume in our system. Our equilibrium reaction is 6 milliliters, or 0.006 liters. So the expressions that go into equilibrium constant, PR and ME, the concentrations, those are calculated in this way. How about the other two? Okay, we're going to do a calibration curve here, and we're going to monitor the concentration of the blue species. How do we do that? Blue. So it's COCl PR3. Brackets and the plus. Right. So we'll provide you a concentration of, we'll tell you this is 0.01 molar COCl PR3 square bracket plus. We'll give you that concentration in a PR solvent, in propanol. So blank the instrument with propanol, and then we'll add small aliquots like 0.1 milliliter of the standard. We've done this times. This is the third time we're doing it. So in that way, we start with a blank PR, and we add this complex ion that's dissolved in PR. It's concentrated, so we add small aliquots. We should see the blue color intensity increasing, and from that measure the absorbance, work out the concentration, and come up with the calibration plot. There it is. It's 610 nanometers or whatever it is. All right, so it just means that with our calibration plot then, when and if we measure the absorbance of an unknown solution, then we can figure out what this concentration is. Remember, these two here equal the slope in our calibration plot. But at the present time, we won't care about those. So if we know the absorbance, measure the absorbance, we calculate the concentration from this equation. Concentration of what? Concentration of the tetrahedral one, the blue one. So then let's perform the experiment. We want to determine Kc as a function of temperature. So we're going to change the temperature. So make our equilibrium mixture. What does that consist of? 3 milliliters of the standard solution of COCl PR3 plus, right? That complex ion, the tetrahedral complex. 2 mils of PR and 1 milliliter of Me. Haha! What we're going to do is take that and put it in an ice bath. Well, not a regular ice bath, a dry ice acetone bath. Dry ice and acetone, make a slush of that. The temperature is very cold. Minus 50. Actually, I don't know what it is. Minus 40, it's some low number. Really low. Minus 50. Hey, you can Google it up and find out. But anyway, we're going to take our equilibrium mixer that way with tongs, because this is really cold. Dip it in and let it sit there until we observe the blue turning completely to pink. Aha! So now we've shifted the equilibrium to the right hand side. It's all pink. Then we'll take it out. Put in a calorimeter. Put in a temperature sensor so that it doesn't interfere with the measurement light path. Right? Duct tape it, and so can measure absorbance as a function of temperature. Now, how will the temperature change? This system will warm up automatically from the much higher room temperature. Heat going into the system from the room, and so with that, the temperature will increase, and we can record absorbance as a function of temperature. And then, of course, we can do the calculations. So here's what the setup looks like. 1.5 centimeter of this going in. That will ensure that it doesn't exceed the path length, block the light. And then, of course, so put a little stirrer here, with a little stir bar in there, so that as it warms, we're mixing it slowly, not creating a vortex, because that will disturb the absorbance, but kind of just nice and slow here to make sure that the heat coming from the outside kind of mixes in. And then you record the temperature until we're done. So here's the idea. Do it once, do it twice, do it 3 times. That's how you know things are reproducible and good. Don't do an experiment once and think, ha-ha, I'm in heaven already. Wherever heaven is. Really, no. You feel okay and scientifically confident if the data and the results are reproducible. So that's all up today. Watch out for these solvents. We don't want methanol or propanol or whatever entering in anybody's eyes and skin or whatever it is. So again, watch out for that. Calculations are again pretty straightforward. From the calibration curve, you solve the equation and determine the concentration of the tetrahedral species. Then if you know what that is, this is a tetrahedral species, then you can figure out what it is. We'll know what this concentration is from the start. If we saw a change is X, and from the calibration graph we know what this X is, we saw for X's in the concentration, then we can backtrack and figure everything out in the same way. So of course we talked about these two are done already. That's done. This one is done. This one comes directly from the calibration plot. How about this one? Well, if we figure out the starting concentration or the starting number of moles, then we figure out the value at equilibrium. Then the difference is what's actually reacted, and that's equal to the number of moles of the other one there. So via that, so I like to do it in moles. So if this is moles of this to start with minus moles of equilibrium will give me moles of this, and divided by the total volume of the solution will give me the concentration, and that's the number that goes here. And then in Excel you can then perform the calculations. This is a lab that you couldn't do manually, so hopefully you'll sing the praises of Excel here. After a little programming here and there and checking, then you can copy and paste and process a lot of data. So with this in at the end of the day, we should be able to come up with delta H, delta S, the various KCs, but that's not important. And then from the thermodynamics, we can determine delta G at any temperature, because delta G is equal to minus RT ln Kc, which is equal to H minus T delta S. So how can I do this? Well, if we determine Kc is a function of temperature, if we take this equation here, let's this part here, we can reorganize it to derive this. That indicates if we plot ln Kc versus 1 over T, then the slope is minus delta H over R, and the y-intercept is delta S over R. And so if we know those from the plot, we can certainly do the calculations. There it is. Yep. R is 8.13, the usual R. So that's all up this week. Just about time management. This lab doesn't take long. When I devise labs, I have your welfare in mind. I want to be spending forever at this stuff. You guys have a life to live. Not only those other crazy subjects, math, psych, me, yeah, they're all good. They're all good. Chemistry comes first. Joking. But anyway, time management here. I do these labs that if you sit down and do the lab, complete it, and go to your Excel right away, you should be able to complete the stuff and hand it in within 3 hours. Working with your buddies from the lab, you go much faster on various things, and you will check on each other. Your grade will be better. You'll be done in 3 hours. Be a much happier student. If you go home and go elsewhere, whatever it is, who knows when you do it, and you have more challenges at that time than you would if you had followed my advice. happy learning, everybody. Bye-bye.